We'll start 3 minutes past the hour. Okay, so we'll start now. So I guess many of you have who are attending this lecture have heard about gravitational waves. Uh, it made a lot of headlines in the recent times. In this lecture, we will get a very brief overview of what is going on in this field, and you can get some ideas of whether which may help you to decide whether you want to explore more, to see whether you want to work on in this field and so on. So you can ask questions at any time you want during the lecture. So I think you can raise your hand, and then I will, as soon as I notice it, I will get back to you. Okay, so there will be three lectures, as you know. The first one will be origin and sources, second one on detection, and the third one on the present status of the field and the future prospects. Okay, so the field of gravitational wave astronomy essentially, uh, the 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 primary milestone, you can call it like the birth of the gravitational astronomy, happened with the detection of the merger of a binary black hole. Two black holes went around each other. They emitted gravitational waves, which were detected in two detectors in the United States, which are about 3,000 kilometers away. Then they merged and formed another bigger black hole. And this whole part, the signals, the predicted signal from these events, from theoretical consideration, basically general theory of relativity, matched the signals which were detected in these two detectors, which were so far away that it is very unlikely that they were caused by some instrumental artifact. So this was considered one of the greatest discoveries in the century, for which Rainer Weiss, Barry Barish, and Kip Thorne got the 2017 Nobel Prize in Physics. This uh, discovery was done by, of course, the contribution came from 1,000 people across the globe, and these are kind of marked here. As you can see, there are a lot of points in India also, as several Indian scientists contributed to this activity. What exactly happened, why, how we detected, and so on, will become clearer in this activity. So right now, several sources have been detected. About 100 sources have been detected by nearly, not exactly, but which are mostly binary black holes, and then very few mergers involving neutron stars have been detected, and only one binary neutron star merger. Okay, so we'll start now. This is just to give you the flash the prime highlight in this field. Of course, there are many other things which you will see before we get into the uh, details. Now, the first thing to understand is that why a new field of astronomy is so important. So we have to go back to go back about 400 years back to Galileo. See, human beings have been doing astronomy since I think they started to look at the sky and started guessing uh, from where we came and things like that. But then they were using the eye to observe the sky. Eye is a very remarkable instrument, of course, the human eye, but it is highly limited. The aperture is small, you cannot integrate for too long, and so on. Galileo was a great physicist, and of course, he founded the theory of relativity in the beginning, that is the Galilean relativity. Einstein relativity came later. He also was a great experimentalist. He uh, introduced at that time what was the cutting edge technology available, that is uh, the telescope for observation in astronomy. So with that, he could observe all the phases of Venus, which firmly established that the planets are going round the sun, not that everything is going around the earth, which may appear because of the relative motion. And this was one of the most convincing proofs that that the planets go around the sun, because as it goes around, the its crescents, we see the crescent. So just like the moon grows and shrinks, I mean, meaning in the sense like the lunar crescents essentially. So the same thing happens with Venus, and that can only happen if it goes behind the goes around the sun. I mean, if it was going around the earth, such a thing would not be seen. I mean, it would be kind of frozen. Okay, so the thing is that even though it looks very simple, the human beings at that time also were trying to explain these motions with very complicated mathematical model. That the sun could be at the center and the planets could be going around it was already proposed, but then without an experiment, it becomes very difficult to prove things. And that is why observation becomes so important in astronomy. So then, after Galileo, there has been, so that was in the optical wavelength, and there are a huge number of bands in the electromagnetic spectrum. I mean, each of these bands are also subdivided. In this, we have done several observations, and then these are some of the state of the art observatories there. This was Galileo's telescope, and here we are today. You can see that these are the uh, cake telescopes in Mauna Kea. This is, of course, I should now put JWST also. This is Hubble Space Telescope. This is Chandra X-ray Observatory. This is Swift Gamma Ray Observatory. This is Planck CMB mission, and this is GMRT. So all those things were done in the following more than 400 years. And so the point I'm trying to say is that from here to here, we have made a absolutely dramatic improvement in our understanding of the universe. So now, Galileo saw some of the planets, some of the not only the planets but also their satellites of Jupiter and so on. But now we have a very precise view of the image of the solar system. We have very good pictures of the galaxy. I mean, these pictures may not look very uh, anything exciting to you anymore, because we all the time we see these nice pictures. They come everywhere. But I'll tell you later that why even 100 years ago this was not imagined. People actually thought that the Milky Way may be the only, maybe the entirety of the universe. There may not be anything beyond it. They could not imagine that there could be other galaxies outside. And now we know, and now these pictures become trivial to us. But what I'm talking about is less than 100 years ago, when people were flying aeroplanes and so on. So this is how dramatically astronomy changes with observation. This is a picture of the Sloan digital sky survey. Basically, this is a slice of the universe seen from the Earth, and you will know more about it during the summer school. This is a supernova remnant, and this is gravitational lensing. All these things essentially gave us meaning. This came from modern astronomy, modern instruments, and they completely, as I said, dramatically improved our understanding of the universe. But then the astronomy goes beyond that. These are it is not just we got better and better picture, but our understanding changes very dramatically with serendipitous sort of discoveries. So these are some of those examples. This is a pulsar, which probably you have heard that people did not know such things exist. And when signals from the spinning neutron stars came to the Earth, people started guessing, are these from some sent by some aliens from some other civilizations? These are some of the giant jets that are coming out of these galaxies. This is the cosmic microwave background. All these things people did not know that such things exist. This is the picture which shows that the universe is accelerating, which got a Nobel Prize also. But even that, actually, all these three got Nobel Prizes. Even before that, when it was proved that the universe is actually expanding, even people like Einstein refused to believe. But then now we know it is not only expanding, but also accelerating. So the point here, okay, let me show one more slide and then we'll conclude this part. So you can see that in 1920, that is, okay, it's more than now 100 years ago, people used to think that our galaxy is the universe. This is, you can see in Wikipedia. So there was this great debate going on. Then Einstein thought the universe is static. He thought that how could the universe be expanding and things like that. Okay, so the point here is basically that when a new field of astronomy comes, it's a there not just we have a more high resolution picture of the universe, but there are paradigm shifts in our understanding of the universe, and that's what we expect also from gravitational wave astronomy. But it has already started. People did not know that black holes can be so massive, and the massive black holes are so abundant. People thought that black holes are probably going to be few solar masses, but that there are tens of solar masses of black holes, and they are very abundant in the universe. Well, some people predicted it, but the thing is that there are many other things which were also predicted. This is only with observation, this feeling, this understanding changed so dramatically. Okay, now we'll start with some of the basic concepts. And as I said, you can always raise your hand and ask questions. Feel free to interrupt. Okay, so the gravitational waves are predicted by general theory of relativity. In fact, any relativistic theory of gravitation can predict gravitational waves. Now, what is a relativistic theory of gravitation? So, you all know Newton's laws of gravitation. I mean, maybe some of you or most of you did not have a course in general relativity yet, and probably you could only have a general relativity course perhaps in your MSc if you choose a special paper. Normally, you would not learn general relativity. Now, what happens in Newton's laws is that you know the famous formula that if there are two objects which are let's say r distance away and the masses are m1 and m2, the force between them is m1 m2 by r square times g, the universal constant of gravitation. The problem here is that this formula does not involve any time. So if suppose one of those objects suddenly disappeared, or let's say it was a particle antiparticle uh, pairs which were kept close, and then suddenly somebody opens a valve, they combine, they become, say, photon which are massless, then immediately the other object understands that there is no force anymore. So it was experiencing, so both the objects were attracting each other, and suddenly this one disappears or becomes massless, and this one immediately feels that effect. So there is a problem, that it should not, it violates the principle of relativity, that the information travels all at infinite speed. So Einstein wanted to develop a theory, a relativistic theory of gravitation, where these kind of problems would not be there. He already developed the special theory of relativity, which combined electricity, magnetism, and space and time in 1905. And then he wanted to develop the theory of gravitation, relativistic theory of gravitation, which took more than 10 years to do that. Now, general relativity, of course, is a vast subject, and it takes almost at least half semester course to learn general relativity. But I will tell you the glimpse of it. So this is essentially I think you already had the lectures of general relativity, so I don't have to get into it so much. So basically, the point here is that just to summarize, that space-time tells, this is Wheeler's word, tells matter how to curve, how to move, and matter tells space-time how to curve. And essentially the thing is that, just again, this small summary is that it is the geometry of, so space-time gravitation is described in terms of the geometry of space-time, and this geometry is determined by mass and energy and their movement. This is what general relativity essentially is. Now, general relativity predicts things like black holes, that is event horizon, and so on. So there are, you could have a Newtonian concept of black hole, but general relativistic black holes are different. For example, in a Newtonian black hole, if you put a mirror and shine a light, light would reflect back. But that is actually not the case for general relativity. And also, general relativity predicts gravitational waves. So this, in case there are some students who already actually studied general relativity, this slide is for them. I mean, others can also follow. I mean, there is not much mathematics that way. I mean, I'm not going to prove anything, but essentially, this I mean, you have seen this equation in the gravitation, in the general relativity lectures. That Einstein's equations describe the this how that line I said, that how matter curves space-time, and space-time tells matter how to move. And these are highly nonlinear equations and very difficult to solve in general. However, in this particular case, suppose the metric is nearly flat. It has a background which is nearly flat, plus some small perturbations in it. If you substitute this in this equation, then you get a linearized equation of this form, where this is something called a trace reverse metric perturbation. Now, if you solve this, okay, let me see, there is a chat message here. Okay, there is a question. I'll come back to that. So if you solve for this, there you can like Maxwell's equations can be solved to get the field to get the fields everywhere, and with and without sources. That is, if you put sources, then you get one solution, and if you don't put the sources, then you get the vacuum sort of propagation solution. So this is the, if you put the right hand side to be 0, you get a solution like this, which in the right coordinate system. Just a moment. Yes. Actually, my lectures. Yeah. So if you this is basically in a specific coordinate system. You can write the metric perturbations in this specific form, where the diagonal components are represent. So you can see that this has only 4 components, and these diagonal components are essentially the same. It's the negative of this one, and these components are the same because this matrix is symmetric. So basically, there are only 2 independent components, H plus and H cross, which describe the whole perturbation. So basically, this means that gravitational waves have only 2 polarizations. This is this holds even in other coordinates, but in this specific setup where the wave is propagating along the z-axis and this specific coordinate system, it becomes explicit that there are only 2 independent parameters here. Okay, there is a question which says that what do I mean by Newtonian black hole? So it is those kind of and whether those kind of black holes are possible. No, Newton. This is just from Newton's laws. We don't think such a black hole is possible. But if you could get a formula for black hole using Newtonian considerations also, where you could basically find the escape velocity, you will see at which density, that is the, okay, let's say that what kind of mass and radius an object should have, such that the escape velocity becomes the velocity of light. And that will basically tell you, give you some concept of black hole. But the problem with that argument is that if you put a mirror on that and shine a light from distance, because light is going to speed up somewhat, I mean, in that consideration, then it can also reflect back, which is basically, then it is not really a black hole that way. In a real black hole, no matter you shine light from outside or from inside, it basically becomes extremely slow near the event horizon. It simply cannot cross the event horizon to an observer who is sitting outside. Okay, now moving forward, I mean, of course, that is kind of related to general relativity, but yeah, since I said that, this is okay to mention. So we move more in the direction of gravitational waves. So what are gravitational waves? These are again transverse waves like electromagnetic waves. They travel at the speed of light. Again, like electromagnetic waves, they have 2 polarization states, which is also like electromagnetic waves, other than the fact that electromagnetic waves have polarizations at 90 degrees. But for gravitational waves, they are at 45 degrees. And you will see what I mean by that. Gravitational waves interact very weakly with matter, which has the advantage that they travel long distances without losing any information. Hence, it becomes very hard to, so that is the advantage part, that they can come from very dense region of the galaxies and so on, where the dust cannot block them. But it becomes very hard to detect them, that is why it took more than about 100 years to detect gravitational waves after their prediction. But on the other hand, this is overall good, because we could build more and more sensitive detectors, but we cannot clear, let's say, the galactic dust or something. Now, after the first detection, there is huge worldwide effort going on to develop gravitational wave astronomy, but we'll come back to that later. So these are some of the comparisons for gravitational waves and electromagnetic waves, which can make it more clearer to you. So there are many similarities, like space is the medium for both. Now, for electromagnetic waves, generally, what we talk about is incoherent superposition of photons, or light, which are emitted by atoms and molecules. For example, when we are looking at any light source, let's say right now you are looking at your computer screen. So here you are looking at some kind of stochastic radiation. That is, you don't know which atom or molecule is emitting at a given time, but you are basically seeing a overall brightness of different colors from different parts. But for gravitational waves, when we are talking about generally for this, for what has been detected and what we talk about in general, are coherent, are coming from coherent motion of big masses. That is like two black holes going around. Okay, so this one is more like a coherent radiation. It is almost like one single atom emitting something. But this is these comparisons are kind of loose. It is not like it is absolutely the case. There is the stochastic gravitational background, which is created by a large collection of astrophysical objects, which can also emit gravitational waves. So these are also there, but these are like loose comparison. That what we mean when we generally talk about them. Then the wavelengths we talk about electromagnetic waves is usually very small. Uh, like optical wavelengths are, like in angstrom and so on. But when we are talking about gravitation, I mean few thousand angstrom, sorry. So when we are talking about gravitational waves, we are talking about very large wavelengths. So so let's say that the waves which were detected for the first detection were around 100 hertz. So which corresponds to, since they travel at the speed of light, so if you take 3 lakh kilometer divided by 100, it is basically about 3000 kilometers. So obviously those wavelengths are extremely large compared to what we generally talk about in the context of electromagnetic waves. They uh, and this I already said that the interaction between gravitational waves and uh, normal objects is extremely weak, which is why even though gravitational waves are passing through us all the time, we cannot feel it. It's extremely small. On the other hand, that we can see something, right now we are reading this, is because photons can interact very strongly with matter, and in this case, the eye, and which is why it becomes very easy to observe using photons. So again, just like the wavelength is large, obviously the frequency is very small for gravitational waves, generally what we talk about, and very much higher for electromagnetic waves. Okay, I think yeah, this is good enough to mention. Then the directionality of the antennas. So you see that when we talk about telescopes, even radio telescopes, we generally say that something which can be pointed to different directions, like a dish antenna can be pointed, a telescope can be pointed. But for gravitational waves, they are detectors on the earth, as you will see so far. So it is very difficult, and they are omnidirectional. You cannot really point them to a particular direction. So they are kind of like dipole antennas, which are also used in electromagnetic astronomy. So they are like small antennas, dipoles, and then you can make a array of them to localize a source on the sky, which is possible with gravitational waves. But this antenna network is also possible with directional telescopes in electromagnetic astronomy, and you will learn more about that in radio astronomy lectures. Okay, I think these are kind of general uh, comparison. If you have any questions, please let me know right now. I'll just pause for a few seconds. Okay. Now I'll move on to some of the most um, some of the sources which have been predicted. Acha, okay, there is a question. Uh, is so the question is that is destructive and constructive interference possible in gravitational? Yes, absolutely possible. Gravitational waves have all the properties like electromagnetic waves. So they can interfere, they can get lensed, and all those things can happen. They get redshifted. So these are basically like electromagnetic waves. Okay, one more question is, can we bend space-time by any means? Yeah, I mean, like if you the earth is bending space-time, and that is why things are falling into it. You can, if you send two massive objects far away from the earth, then they will, let's say that they are very far away, so that earth's gravity does not influence them anymore, and these two are massive objects, then they will start bending space-time in the neighborhood, and they will start influencing each other. Then there is a question. Okay, so his other question is that without using mass, yeah, you can do it using energy, for example. Energy can bend space-time as well. What can bend space-time is gravitation, and that is so nothing else. Then there is a question: is smaller wavelength uh, good to obtain high resolution? That is right, sort of. So the resolution is determined by is like the Rayleigh criterion, that by lambda by d, where lambda is the wavelength and d is the diameter of the telescope. So smaller the wavelength, higher the resolution, but larger the diameter of the telescope, also you have higher resolution. So in principle, optical, uh, in optical wavelengths, you could get very higher resolution than radio telescopes. But on the other hand, radio telescopes could be very large, because especially if they do interferometry, it can be separated by several kilometers. So you could effectively get higher resolution than normal optical telescopes. So these are all possible. Uh, there is an interesting question. Somebody says that do gravitational waves uh, also show dual nature, just like electromagnetic waves? So we have not. So we do not have a quantum theory of gravitation yet. We don't know whether gravitation is quantized or not. So we don't know whether gravitons exist or not. So for the time being, what we detect are classical waves. Uh, then there is a question that why polarization of gravitational waves is at 45 degrees. So that we will see soon. It is just, there is nothing like why. I mean, this is how nature is. I mean, if you look at, if you solve Einstein's equation, which is proven experimentally, there is no other way to prove that Einstein's equations are right, and maybe they are not at some limit. But with that, if you, when you derive gravitational waves and if you see the properties, then you see that they are at 45 degrees. That is when they. So I'll show you some pictures later on. Then there is a question that how you come to know for the first time the waves you detected is gravitational waves. Well, the thing is that gravitational waves are predicted for a long time. I will come to the detection part later on, and different the effect of emission of gravitational waves, as well as what happens when you detect when they fall on a detector which is designed specifically to detect them. In both cases, predictions were there and they matched, and then it was ruled out that the detected waves are generated by some other instrumental artifact. So then you know that these are gravitational waves. Like, you don't see everything, right? I mean, for example, how do you know that you are seeing infrared with using a camera? Or how do you know that you, like, for example, there are these high energy experiments where different things get detected. You don't feel them, that the instruments feel them, detect them. And you could always ask, oh, well, then maybe the instrument is seeing something else. Uh, okay, what are the applications of gravitational waves? Well, there are no applications of gravitational waves in the sense that if you want to apply gravitational waves of something, but then what is the application of mankind? So it is very difficult to say this. So maybe our purpose is to acquire knowledge. That's the primary purpose, and gravitational waves can be used to serve that purpose. Uh, of course, in the process of, like in astronomy, that in any field of astronomy, when you you try to develop experiments or instruments to see to understand the universe better. But in this process, you create several things which become kind of part of day-to-day life. For example, many of you must be uh, using Wi-Fi, which was basically developed by astronomers because they wanted to send signals from one radio telescope to another. Then there are, let's say, CCTV cameras, which are used in your mobile phone or many other devices for capturing pictures, which were developed by astronomers. Then, I mean, I'm giving you examples. Of course, there are much bigger uh, applications like in weather predictions and so on, which people used to do using different things with astronomy calendars, which are far more important applications. But then day-to-day life you are using, for example, the maps you use, like Google Maps. You know, many people use that. So which requires a correction from general relativity. The GPS satellites would otherwise give you very wrong predictions. So then, one could ask that what is the use of gravitation or general relativity, because it is only Newton's laws were enough. But then the applications come much later, and also applications are not very important. I think to me, the acquiring knowledge is far more important. Uh, so there is another question. Since gravitational waves are the speed decreases when they travel from light emitted. So the thing is that in if gravitational waves are so why does it happen in case of light? So there is constant absorption and re-emission and so on when it goes to the media. For gravitational waves also it could, but I don't know if such a dense medium exists in the nearby in the universe. Okay, okay. So there are many questions. So let me answer one by one. Why gravitational waves are transverse? Why gravitational waves are not longitudinal? Well, that is what comes out of the equations or governing them, meaning why electromagnetic waves are transverse and why they are not longitudinal. It is exactly the same answer because they satisfy the same kind of equations. Um, can we produce artificial gravitational waves? That is an interesting question. So this is not that. So generally, if you try to wave your hand or take two very massive bodies and move, then there is it can generate gravitational waves, but it will be extremely weak. You would not be able to detect it. All the time we are generating gravitational waves. Like for example, my two hands are also attracting each other due to gravitational forces, but it is extremely weak. I mean, they are, of course, the force is there, but it will be very weak. But there are attempts, there are plans, people are exploring that if we can generate, we can rotate two objects, not two objects, basically array of objects, but in pairs. Like say, two objects are moving in certain way, and you do exactly the same in another two objects. So basically, you create an array of phase coherent emitters to see whether that can be added up to create some detectable gravitational waves. Then there is a question that gravitational waves travel faster than electromagnetic waves. Well, no, they travel at the same speed. But then, if there is a refractive index change, then yes, light kind of can slow down. There is another question that we can say that gravitational wave opens another window besides the electromagnetic waves window to observe the phenomena involving high mass celestial objects. Yeah, this is also an application that is certainly an application for acquiring knowledge. Yeah, I think that is perfectly a good reason. And of course, we can see not just high mass celestial objects. There are many other things which we may be able to see. For example, the waves from early universe. So we'll come to that very soon. So there is another question that how gravitation will help in understanding the universe. Will it? Yes, that is true, and many ways. We'll come to that very soon. Okay. I think especially in the last lecture there will be more discussion on that. Apart from CBCs, what are the single body sources that can generate gravitation? We are coming to that in two more slides, probably. Can we use gravitational waves for telecommunication? This is so we are unable to generate gravitational waves so far in the lab, meaning we can generate, but then detectable amount of gravitational waves. So it will be difficult to use them for telecommunication for the time being. But maybe at some point. Right now we use radio. Uh, is there any theoretical proof that gravitation will travel with C? That proof is actually pretty straightforward. I mean, it is. I already showed you the equation. So you see this box of h mu equal to 0 is what you are going to solve. This box is the same box that comes when you write the wave equation from Maxwell's equation. And basically, this is the Dalavar upward vector, which has 1 by c square del t square minus nabla square, that kind of thing. So that 1 by c square basically determines the speed. Meaning any wave equation will have a solution where this 1 by v squared term determines the speed, and in this case v is equal to c. So that's how it comes. Then there is another question that whether we can use gravitational to measure distance of objects in space. Yes, we can use, but not by sending. But when we receive gravitational waves, we can say very accurately, quite accurately, what is the distance of the object which has emitted the waves. But not like sending something and then catching a reflection, because that would not be possible right now, because we cannot even generate a measurable quantity of gravitational waves, and then also finding a reflector for gravitational waves. I mean, it may not be even possible. Okay, now moving on. So, okay, first let me come to this. I'll first describe what it is. So, the primary sources of gravitational waves are is the most important source, of course, is the compact binary coalescence, where two objects go around each other. They emit gravitational waves. As they emit gravitational waves, to compensate for the lost energy, they have to come a bit closer. When they come close, their frequency goes up because they start moving even faster, which creates even more gravitational waves. So this is a kind of an avalanche process. It's a non-linear process. So in the end stages, it emits extremely large amount of gravitational waves and then merges. So the thing is that in the initial phase, it could be when they are far away, this part could be modeled kind of analytically. The next part, when they are really merging, is very complicated and it has to be modeled only in supercomputers. And then the final part is the ring down part. So where the final black hole settles down, which is like a part of black hole, and this part can also be sort of handled analytically. Okay, now then there is a question that can gravitational waves be used to detect other universes to support multiverse theory? I think we are quite far away from that. Yeah, maybe some signatures of other universes are imprinted in primordial, that early universe, stochastic gravitational background. But yeah, let's see. But we are at a very basic stage now. We have to first detect some of the the nearby universe. Then maybe we will reach there. Okay, so this is a simulation which kind of shows how the gravitational waves uh, are produced. So these are two black holes, and you can see that as time progresses, both the amplitude and frequency increases. So see, the wavelength is reducing and amplitude is increasing. So this also happens for birds sound, and that's why these signals are also called chirp signals. Then they merge and there is a ring down phase. Now, in this, there are some formulas written here. You can see that the strain signal produced by these waves. That is, when gravitational waves fall on matter, they create a distance fluctuation. Suppose something had length L, the length would change by delta L, and this delta L length change would be proportional to the length. So if you take the ratio, then that becomes it can be a dimensionless number, which is kind of represented by this h. I mean, of course, the actual wave is time dependent, space dependent, and so on, but this is the kind of estimate for the amplitude. Now you can see that it increases with mass, it decreases with uh, the period, with frequency. So basically, uh, as the period increases, the amplitude decreases. Yeah, and as the frequency increases, the amplitude increases, and also with distance, like standard 1/r. And this is for one kind of source, meaning mass parameters. This is for other kinds. So here, these are long duration in spirals. That is, the sources are very far away. But here, they are almost near marching. So it is like 100 hertz frequency. So this kind of thing. The important thing to see is that this uh, these numbers are very low. Okay, somebody wants to see the animation again, so I'll play it for that person while describing this. You see, these strain signals are very low. So what it means is that even if you have a 10-kilometer long detector, the the amplitude, that is the fluctuations that will happen in that object, or maybe you have two free masses which can oscillate, will be extremely small. It will be like 10 to the minus 18 meters, that is smaller than the size of a proton. So that is the kind of perturbations that are created by gravitational waves, which is why it is so difficult to detect them. Okay, so even though those are the only sources which have been detected so far, there are more sources of gravitational waves which are predicted. Essentially, if you have the mass quadrupole moment of a system varying with time, then the second derivative of that gives you the estimate for gravitational waves. You can, if you are interested in this, then you can also read up and so on. So this is basically, you can see the kind of the retarded time, which, and then you can get all these things. I mean, these are available in standard text. But then what kind of systems have a quadruple variation? For example, if you take a perfect sphere which is spinning, it does not have any quadruple variation. So it's not going to emit any gravitational waves. But if you take a perfect sphere with a small, let's say, bump on it, and it starts spinning, then the quadruple does vary. And that is what happens for, let's say, pulsars, spinning neutron stars, etc. Okay. Now, then there are other sources. I'm just mentioning a few. There is, for example, supernova. So if there is a supernova explosion, there could be some part of the energy which would be converted to gravitational waves, especially if the supernova is not perfectly spherically symmetric. And that maybe we'll be able to detect one day. Then there could be supermassive black hole binaries. These are almost like, okay, so these are much bigger sources, and they can be detected by, let's say, space-based detectors. There could be a small black hole going around a supermassive black hole. So supermassive black holes could create continuous waves, like when they are very far away. But a smaller black hole can be closer to the supermassive black hole, and still it can create continuous waves. It depends on which frequency you are looking at. For example, supermassive black holes can merge in let's say, space-based detectors. You will see where they are in millihertz band. But if you have a detector, let's say pulsar timing array, which works in, let's say, 10 to the power minus 9 hertz, there these sources may appear as continuous wave sources. Okay, there is a question that why the pulsars magnetars are continuous sources. They are called continuous because they are spinning all the time. Okay. On the other hand, a merger is like a very short duration signal. It can be less than a second in duration, because only that small part of the time the wave becomes detectable enough because of this non-linear growth. For pulsars, it's spinning all the time, and then the signal is basically like a monochromatic wave, but except for some glitches which can happen occasionally. Can we identify any properties of the resulting black holes from a merger? This is another question, and it's GW other than its mass, like charge in rotation, charge in rotation. So I think you were pointing to something called the no-hair theorem. Yes, that is one of the things that is which is a primary science goal for gravitational waves. That when two black holes merge, they form a bigger black hole. the bigger black hole then emits this ring down signal, this damped harmonic oscillation. Like, when you ring a bell, it goes down like that. So that kind of signal. Those signals are supposed to be the functions of dependent on only on the mass and angular momentum of the black hole. I mean, also could be charged if it is charged, which may not be the case. But then, but if we measure those, if we can measure those uh, parameters of this ring down, that is the damping and time and the frequency, from there we may be able to say whether those parameters are dependent only on the mass and angular momentum of the final black hole. And that would be a strong test of Noether theorem. And if it is violated, then we know that there is something wrong with general relativity. Another question is that why it needs to be spherically symmetric for no production of gravitational waves. Now, if it is spherically symmetric, okay, you can do these calculations yourself. So you take a complete sphere, you take a sphere and make it spin. You will see that its quadrupole moment does not change with time because it is symmetric. Then the question is that where is the charge, sir? Where is the charge distributed on a black hole if there is nothing there? Let's say a Schwarzschild black hole. Well, we don't know what is inside the black hole, but a black hole can be charged or may not be charged. It's so you are thinking like a conductor or something. I think the charge does not have to be on the surface, but we would not know where they are inside the black hole. Does gravitational waves get reflected? Okay, we don't know. I mean, they can in principle, but then we don't know what can reflect gravitational waves. Like it is very much like electromagnetic waves. How does electromagnetic wave get reflected? You can, if you can, you can probably try to map it there. Every property is followed, but then getting something to reflect gravitational waves, I think you have to really construct something really theoretical. It's not may not be possible in nature. Okay, so there are more sources of gravitational waves like stochastic sources. I think I already mentioned that it could be a collection of these individual sources which are localized in a certain region, and then you don't know which one. Like I know the example I gave for normal electromagnetic waves that you see from a light bulb or this computer screen and so on. So there, you don't know which source is emitting when, but there is a collection of source which makes it generally bright in gravitational waves. I mean, this is basically in electromagnetic astronomy. These are the kind of sources we see, not the kind like binary merger kind of emission and so on. Now, the thing is that there is another source which is generated in the early universe. So when right after in the very early universe, let's say if there was a phase where the universe expanded rapidly, it's called cosmic inflation. At that time, there could be some gravitational waves which were produced due to some of the mechanisms, which are still there right now, and if we can detect them, then it will be kind of a smoking gun test of cosmic inflation. Okay, so these are some sources of gravitational waves, and they span different frequency bands. Right now, we are in this band, the LIGO band, which is coincident. So it's an interesting coincidence that it spans the a part of the audible frequency band. Okay, they start from, let's say, around 20 hertz and goes up to few kilohertz. This is the band. What have we seen there? So neutron star, black hole mergers. It could be neutron star, neutron star, black hole, neutron star, black hole. All those things which we have observed so far. There could be supernova core collapse signal. That is where the supernova just collapses, and that it could generate there. So these are the kind of sources we expect. There could be pulsars and so on, like spinning neutron stars. but we may not be able to reach the sensitivities with the present generation detector. We may need next generation detector to observe them. And then at the lower frequencies with a space-based detector, we will see later that you cannot use a ground-based detector to really see below, let's say, a few hertz. You have to go to space. And with the space-based detectors, you may be able to see supermassive black hole mergers. There, in fact, the stochastic background, which we have not been able to detect with LIGO yet, the binaries, the white dwarf binaries in our own galaxy can create a confusion noise, a background of signals which are unresolved. So those things can happen also with LISA. Okay, so I think here I will stop here today. If there are more questions, I can answer. So the point here is that there are different kinds of sources of gravitational waves. We have only detected some of these mergers in one frequency band, but there are multiple frequency bands, different kinds of sources, and that is they are yet to be detected, and even probably some of them yet to be predicted, and that is very much that is understandable, because this is just the beginning of this new field of astronomy. Okay, now let me see. There are more questions. If we can have charged rotating black holes, we can perhaps see coupling of electromagnetic and gravitational waves. Has it been tried? I'm not very sure if there is a charged black hole. How gravitational waves are going to interact with charge is not very clear to me. I don't think they will. So, yeah, I mean, if there is a charged black hole, then maybe the metric will have some effect. Yeah, I mean, one can see those. This seems pretty far fetched. Maybe one day somebody will see something like that. So then there is a question that in case of a reflection, then the universe, which contain huge mass and energy, will produce gravitational wave that has the probability of getting reflected from other neighboring universe and should be detected by now. So these kind of things are possible, that if there is a boundary to the universe, then a wave will go and come back from that because of the topology of the universe. So like if you are, let's say, on something like a torus, okay, and then that is higher dimensional torus, and some wave is emitted, it may come back from the other side, and those kind of things are possible. But again, I mean, these are I think we are quite far away from probing those. Can quantum computers help to get solutions quickly for the gravitational waves? Well, maybe. Let's see. I mean, if they make numerical computation faster, then maybe the prediction of sources and analysis of data will become much better with quantum computers. It will okay. Then so that somebody wants this PowerPoint. I mean, of course, these things are all there in Wikipedia and so on. So there is nothing I have said here which is not there. I think Wikipedia has almost probably everything. So you can just look at Wikipedia. So then there is a question that how would the detectors need to be improved to detect gravitational from other frequency bands? Well, we will see. That the next lecture is on detectors. Do gravitational waves also get stretched while traveling through the? Yes, exactly the way electromagnetic waves get redshifted. Gravitational waves redshifted exactly by the same amount. The redshift factor will be 1 plus z. That is the frequency you observe first by the frequency. Okay, the frequency that is emitted divided by the frequency you observe here is the ratio is 1 plus z. Okay, so yeah, so I will explain what is H very soon. Okay, let me do that right now. So the question here is that what is this H? This is the strain signal here. Okay, it is basically the. So okay, let me go back a little more. So these are the perturbations to the metric. What it means, that a metric is like a ruler. That if you have 2 points, the metric tells you what will be the distance between them. H basically is a perturbation grid. So basically it changes the distance. It creates a fluctuations in the actual distance. Even if the coordinate does not change, the light travel time will change by a small amount. So this is, of course, this has many components and so on. It's a whole matrix. But when we are using this H, it is just the overall amplitude for those waves. So it is kind of, it gives you a flavor that how much would be the order of the fluctuation. It is 10 to the minus 21, 10 to the minus 10, or 10 to the minus 30, and things like that. So that is what H is representing here. Okay, is the quadrupole moment arising due to the presence of mass? Well, this is the mass quadrupole moment. So quadrupole is like dipole suppose there is a dipole, electric dipole. What does it mean? It means that let's say it is plus q and minus q, and the distance is d. Then you will say the dipole moment is q into d. Similarly, quadrupole is the second moment, that is, it will be given by x. Let's say the ij component of the quadrupole tensor would be xi, xj. Let's say 1, 2 components. Then it will be x1 is, let's say, x, x2, that is the second component, let's say y. Then it will be xy rho, which is the mass the distribution at that point, and then you integrate over the whole volume. I think quadrupole moment formula you will get anywhere, but it is the mass quadrupole moment. So it could be mass energy, let's say, but of course mass, the presence of mass is necessary for that. Okay, why do we not make detectors that exactly fill the frequency band? Why do you want to waste the space? I did not actually understand this question. Okay, let me move forward. When we receive a gravitational wave signal, how do we understand it is from a neutron star merger or black hole neutron star merger? Yes, that is a very good question. So the thing is that this pattern that you see on the screen depends on the masses. Okay, when we receive, when we so this characteristics basically tell us whether it's a black hole neutron star, or neutron star. There are two more things. A neutron star merger can also create electromagnetic radiation, which we may be able to see. The second thing is that neutron stars are not unlike black holes, are made of normal matter. Black hole is a kind of like a mathematically perfect object. So they have tidal distortion. They go through those. They also have changed the waveform. So all those things together can tell us what is a neutron star versus a black hole neutron star merger and so on. Neutron star is easy because the masses of both the objects are small, like 1.4, 1.4. Then you know that these are, if the total mass, which is determined very accurately by the measurements, then you know that it has to be a neutron star merger. But if the total mass is large, let's say it is like 10 solar mass, then it could be two smaller size, two like nearly equal size black hole, or it could be one small neutron star and one larger black hole. So there it becomes difficult to say actually what we have seen, and this difficulty persists in the present analysis, but with time it will evolve. Even though it is not that we cannot say at all, but it is difficult to say exactly. Then what is the difference between LISA and LIGO will become clearer in the next lecture. How can we locate the source of gravitational waves? That also will become clearer in the next lecture. Can I talk more about resolved galactic binaries, supernova, cold collapse, etc.? These are simple things. Okay, so the resolved means that when we can individually identify a source. And unresolved, basically what I talked about is a galactic uh, background which is created by white dwarfs in our galaxy. So there are many of them. So it is like it's a continuous set of signals that which is generated. So they are overlapping. So you don't know which one is what. That's all. That's all it means. Supernova core collapse. So supernova can be created in different ways. So the core collapse is like when the star is out of fuel, it cannot sustain the gravity anymore. Then it collapses. That is the core collapse supernova. But there could be other supernova like supernova 1A, where there could be it could be in a binary, and one star could be feeding the other star. So and at some point it collapses. There is an explosion which creates supernova. Uh, One. So there are different kinds of supernova. This you can again read in the. I think there may be lectures here, or you can read in the Wikipedia. Can more about the LISA mission? Yeah, that will be covered in the next two lectures. Okay, next question. I'll come to the hand up now, and then again come back to the chat. Okay. Pushti Shimankar.
Yes, sir.
Yeah,
Sir,
right.
I have one question regarding which you said that EM waves are same as gravitational waves in many in such manner. So we can say that gravitational waves are also the made up of any particles, and which is same as the characteristics like photon.
Okay, so I think it is already I answered. Somebody else also asked the question. The thing is that electromagnetic waves and gravitational waves they have many similarities, which is that they travel at the speed of light in vacuum. They travel in vacuum. They don't need any media. They are transverse and so on. They have two polarizations, but then the polarizations are different and so on. As I said, so that there are similarities, but then there are dissimilarities also, which was shown in that table. The thing is that there are photon is we know that there is a quantum theory of quantum electrodynamics. The theories exist. So basically, but there is no quantum theory of gravitation yet. So we don't know whether there are gravitons or not. We have to wait. Okay, I'll come to Gaurav Bhattacharya a little later. Let me first again answer some of the questions on the chat. For the mass quadrupole moment formula, okay. So that is you could send it to probably the whole group if that is allowed. I mean, yeah, there are many standard book will have that. It is sort of like a moment of inertia, but not exactly moment of inertia. It is the quadrupole moment. Is then there is a question that is gravitational wave can be affected by dark matter. Yeah, gravitational waves can be lensed by dark matter, just like electromagnetic waves can get lensed. That is, they can bend gravitational wave trajectories. Then the question is that could magnetic fields within an accretion disk affect the temperature of the disk? This is not related to gravitational waves actually, but yes, I guess it can. But then there are other lecturers who are going to talk about it. I think. Okay, I come to Gaurav Bhattacharya.
Hello, sir.
Yeah.
Yes, sir. Sir, actually, can you please explain the cause of the perturbation coming in the metric?
The cause of the perturbation. So basically, the if you have moving mass energy, then it is going to change the geometry of space-time, right? Now, when if you try to see the change here when two black holes are merging, that is extremely large. Okay, it can hardly be called perturbation. But then when you are seeing at a far away distance, this change, which has propagated and then reduced, like fall, it falls as 1/r, then it appears sort of like a perturbation. That is the thing. That's all it is. I can explain a little more. Like if you imagine this stretched sheet and you put a massive object there, and there is a small object which you move. So you can imagine that this stretch sheet is kind of creating the a curvature, the geometry of space-time. The small object, like a test mass, is following that geometry. Now, if you this is kind of a simpler picture, but now if you take two kind of comparable masses and then move them, then what happens is that each one of them start influencing the geometry, that is the other particle's motion, and then that other particle also kind of starts influencing this the first particle. So they kind of start affecting themselves in this whole process. But anyway, so this is when they are close, then this effect is much more, and when they are far away, that effect is much more uh, much less. And but the thing is that ultimately they are governed by Einstein's equation, right? I mean, this is sorry, 1 second. Okay. So the last, I think, question here. Is it possible to inject a signal? Okay, by itself with no colored Gaussian noise. Hmm. Uh, so I don't know what exactly you want to do, but then you can inject a signal anywhere you want. Signal meaning, suppose you have a model waveform which you want to inject in some noise you have generated to see uh, like, and then try to detect with your algorithm and things like that. Yeah, of course, those things are possible. It need not be colored. It could be just white noise and things like that. Okay, I think the last question, Akshat Patikar.
Sir, can you hear me?
Yeah, sure, I can hear you.
Sir, in one of the slides, you showed that anything that moves asymmetrically creates gravitational waves. So, what do we mean by moving asymmetrically here?
Right, where the quadruple moment varies, meaning it has to be. So as I said, if it is very symmetric, like a sphere spinning or a cylinder moving about its about the symmetry axis, that is, like if you take a cylinder which is like this, and then this is the axis, right, about which it is axially symmetric, so then there will be no emission. Is that clear?
Yes, sir. Thank you.
Okay. Okay, all right. I think you will. I will stop now. I guess your next lecture will start soon. Okay, then again talk to you tomorrow. Bye.